Welcome everyone to another OCP-TAP call. This is call number 151. I am joining you from Anaheim with the PTTI 2026 conference. Today we have our very own Paul Borrell, and we just go with a short bio as we had Paul also a while ago presenting. Paul Borrell is the founder and the CEO of Daedalus, focused on building simple, reliable, and secure systems for safe digital transactions. He brings decades of experience in system architecture and storage with leadership roles at Sun Microsystems, Quantum, Veritas, and Apple. He's also a co-founder of the IEEE Hot Interconnect Symposium and the Storage Network Industry Association, SNIA. Please join me in welcoming Paul.
Thank you, Ahmed, for that wonderful introduction. I will turn on my video, I think, if I can. 1 second. That way you can all see me. Good. All right. So this presentation, time is not a conserved quantity, and why networks break when we pretend it is a follow-on to the 4 talks I gave in 2024, describing why synchronized time is barking up the wrong tree, and the year of effort we put into Open Atomic Ethernet last year, 2025, so that distributed systems of all varieties and scales can be built to support transactions without leaving a trail of devastation in the data structures and storage devices that we see in today's data centers. Now, this part 1 of the presentation, by the way, there are 3 parts. This one is kind of like the most provocative. The second part is more insightful about the nature of measuring things in terms of bandwidth and latency and that kind of thing. And part 3, I hope, is going to be the most instructive and most mind-blowing part of the presentation. So this is an intentionally provocative title. I want to bring some disciplined physics thinking to the markets and exchanges that we live in, and to, quite frankly, to shatter some illusions that I believe are actually causing harm. So everything we build in networking assumes time behaves like a conserved quantity, something that flows uniformly and can order events globally. That assumption is so deep, it seems like we never notice it. Today, I want to show why this assumption is false and why systems fail because of it. So let's dig into the high frequency trading industry. HFT rests on a powerful claim that markets can be made fair, objective, and orderly through sufficiently precise time synchronization, with, for example, atomic clocks and GPS-disciplined grandmasters, calibrated fiber, microwave relays, and nanosecond timestamps. So firms assert that it's possible to establish a single authoritative ordering of market events. Whoever arrives first wins, and that ordering is presented as a neutral engineering fact rather than as a policy decision. This presentation argues that this claim is false. Engineered simultaneity collapses under physics, distributed systems theory, and market microstructure and emergent behaviors in the market. What remains is not precise time, but a legally enforced fiction that enables systematic extraction of value from temporal ambiguity. The high-frequency trading industry rests on a powerful and seductive promise that simultaneity can be engineered with enough capital, enough fiber, enough microwave towers, and atomic clocks. This is simply not true. At its core, engineered simultaneity is a category error. So Michael Lewis's Flash Boys popularized the idea that markets were rigged by speed and could be fixed by leveling the temporal playing field. The implicit assumption was that there exists a meaningful notion of simultaneous market state that everyone could, in principle, reach. That assumption is incorrect. This book correctly identified latency arbitrage, but misdiagnosed its root cause. The problem is not insufficient synchronization. The problem is the belief that synchronization can create simultaneity in the first place. I've given talks in the past before, and an awful lot of people who don't have a physics background often don't have the instincts for why these statements are not true. Special relativity removes global simultaneity. There is no observer independent now. That's not exotic physics. This is the baseline model that we all already accept. Any system that assumes a globally meaningful timestamp is already operating outside what physics guarantees. Special relativity establishes a hard physical limit. There is no observer-independent notion of simultaneity across spatial separation. Events that are simultaneous in one reference frame are not simultaneous in another. No protocol, no clock hierarchy, no time stamping scheme can alter this fact. Markets are geographically distributed systems. They inherit this limitation, whether they acknowledge it or not. Any claim of global simultaneity is therefore a modeling assumption, not a measurement. Now, general relativity further undermines this premise. Clocks at different gravitational potentials tick at different rates. The atomic clock in the bottom of your rack ticks at a different rate to the atomic clock in the top of your rack, even in the same data center. And if you look at different data centers at different heights, like for example, maybe in a sea level in California, you're going to get a very different ticking of those rates than if you have a data center in, say, Lake Tahoe up at like 6,000 feet. Now, this effect is not theoretical. It's actively corrected in a GPS system. So the HFT infrastructure spans different buildings, different elevations, different thermal environments, and mechanical conditions. Nanosecond level agreement is already a negotiated approximation layered on top of unprovable assumptions about symmetry and stability. The notion of a single market clock is physically indefensible. Just get worse. In quantum mechanics, time is not an observable. There is no time operator. We measure correlations, not time itself. That should already make us suspicious of protocols that treat timestamps as ground truth rather than metadata. In quantum mechanics, time is not an operator like position or momentum. It is a parameter external to the system. Time is inferred from physical processes, not measured directly. So markets are physical systems. Their dynamics arise from interactions. Messages are sent, orders are matched, feedback is propagated. Treating time as a conserved, stampable substance is a category error inherited from classical mechanics and the Newtonian intuition that we all have as human beings. And I have to admit, I had that intuition for a very long time. It took me decades to undo that misunderstanding about the assumptions that I had. So these modern quantum information theory goes actually quite a lot further. I've talked about indefinite causal order in some of my presentations during 2024. So the research by Oshakov and Costa and Bruckner shows that there exist processes with no definite causal order. In other words, these events are in superposition in time, not in superposition in space. So event A is not before or after event B in a global sense. This is not philosophy. This is experimentally realizable physics. As markets become faster, more reflexive, and more tightly coupled, their behavior increasingly resembles systems where causal order and observer dependent rather than globally defined. So as in all my presentations, I'm coming from a distributed systems perspective where we are a software infrastructure company, but we know some things about hardware and physics. The real advantage in the markets is locked into proprietary closed markets overseen by exchanges such as the New York and Chicago exchanges. And high-frequency trading based on timestamps is inconsistent with the physics. This is not about speed. Paradoxically, performance can be far superior if we eliminate this ambiguity with protocols such as Open Atomic Ethernet, which builds a true mathematically correct and physically consistent causal networks. So distributed systems theory has long understood that global ordering is not free. Lamport clocks, vector clocks, and bounded time systems such as Google's true time are approximations with explicit failure modes. High-frequency trading claims to have solved them. It has not. It has merely replaced explicit uncertainty with implicit contractual agreements. Markets are interaction networks, not timelines. Causality arises from message exchange, not clock comparison. By insisting on time-first semantics, HFT repeats the same mistakes long identified in distributed databases and networking. This error is precisely what OCP time appliance projects must avoid encoding into future infrastructure. So a system is fraudulent when it claims physical legitimacy that it cannot have. It exploits asymmetries invisible to the participants and converts uncertainty into private profit. Engineered simultaneity in all three conditions. The industry understands that simultaneity is not physically real, and yet markets the appearance of it as a neutral, objective, and fair. We're now going to dig into a different aspect. Maybe I should ask if there are any questions at this point, if anyone has any on the system, in the audience. I'm looking, so I'll hope that Ahmed will flag me if he sees any hands raised. Kevin, thank you for joining us. It's great to see you. We're now going to dig into a different aspect of this category error and talk about how we unconsciously treat all notions of time as Newtonian and why that creates ambiguous and not quite fraudulent, but because the engineering community really does mean well. But how this facade of Newtonianism is also barking up the wrong tree when it comes to thinking about network protocols such as congestion control and other aspects about how to impose distributed systems on top of this unreliable framework that we call Ethernet. So the networking industry has developed a persistent and damaging ambiguity around a small set of core terms: bandwidth, latency, especially one-way latency, throughput, good put, and bad put. Those words are routinely used interchangeably in marketing materials from the different vendors. Standards discussions, the standards committees talk about this a lot and make some unfortunate assumptions slide. Architectural debates I see all over the place in all the meetings I'm having with many different companies, and even in academic papers, despite referring to a fundamentally different physical, informational, and semantic properties of a network. The problem is we have a semantic mismatch between the APIs at the top of the protocol stack that the applications access and the bits on the wire at the bottom. The result is not merely imprecise language, but a systematic confusion that leads to incorrect system design, misleading performance claims, and broken assumptions at these higher layers in the stack. At the root of this problem is the fact that those terms originate from different intellectual lineages: physics, information theory, queuing theory, and, excuse me, let me just take a sip here, and distributed system semantics. Over time, they have been compressed into a flattened vocabulary optimized for sales and superficial benchmarking rather than careful reasoning. So bandwidth, in its original and correct sense, is a physical property of a channel. In physics and in signal theory, it refers to the width of a frequency band that a channel can support. It's measured in hertz, or in our case, gigahertz and terahertz. Claude Shannon showed how this physical bandwidth combined with signal to noise ratio bounds the theoretical maximum information rate of the channel. Crucially, bandwidth in this sense says nothing about delay or ordering or loss or retries or completion semantics. Completion semantics is the big conversation going on right now. We will be having a special panel at the Chiplet Summit 3 weeks from now to discuss this. So it's an upper bound. Shannon theory is an upper bound on capacity. It is not a statement about what any particular flow will experience. Nevertheless, modern networking discourse almost universally misuses bandwidth as a synonym for data rate, throughput, or even application level performance. So a link in this any network can be described as having, quote, high bandwidth, is usually being advertised as having a high peak line rate under ideal conditions. So this conflation erases the distinction between potential capacity and realized delivery. For example, a 400 gigabits per second link might be one of 4 or 8 lanes in a connection between servers and or between switches is suffering from congestion, head of line blocking, or retransmission storms that do not provide 400 gigabytes per second or anything meaningful to the applications. Yet industry language routinely implies otherwise. Latency suffers from a parallel but even more severe corruption. It is often treated as a single scalar quantity that characterizes delay. The big mistake here is not realizing that it has to be characterized in two-way delay, and one-way delay is completely meaningless in physics. In reality, there are multiple distinct latencies in networking: propagation delay, serialization delay, queuing delay, processing delay, and protocol-induced delays. Those are frequently collapsed into a single route time, which is then abused as a proxy for responsiveness, for synchronization accuracy, or even causality. One-way latency is especially misunderstood. Measuring the one-way latency, as we try to do in synchronized time and in the conferences that you go to, Ahmed, measuring one-way latency requires synchronized clocks with known error bounds. And that's something that is rarely achievable in real systems and fundamentally limited by relativity and causal structure. Despite this, one-way latency figures are routinely published and compared as if they were objective truths rather than estimates resting on fragile assumptions. Even worse is one-way latency is often conflated with completion time. Completion depends upon acknowledgment semantics, on buffering, on retries, and ordering constraints, and failure handling, none of which are captured by this raw transit delay. So the result is that we routinely confuse when something arrived with when we know that it arrives. So that we can't think of time as Newtonian even without talking about causal structure and quantum mechanics. It's already evident in dealing with relativity. So throughput is also talked about a great deal in when people are trying to sell their products into the data center space. Throughput is the rate at which data is successfully delivered over time at some observation point. As Edward Lee would say, every model has to have an observer. Now, unlike bandwidth, throughput is not a property of the wire. It's an emergent property of the entire system for the sender, the receiver, the network, and the protocol, and the workload. So throughput is shaped by congestion control algorithms, buffering strategies, loss recovery mechanisms, and scheduling policies, which everyone has bent their pick trying to get the scheduling policies to give us better results. But we're treating throughput as if it's synonymous with link capacity, This is the category error here in networking. It remains pervasive in both industry marketing materials as well as in system design discussions that I have been involved in. So not all entropy increases failure. Uh, in practice, some of it, particularly in open atomic Ethernet, is the actual transfer of information from one side of the network to the other. So these metrics that we talk about, conflating these link level metrics with the fabric or system level behavior, may exhibit, the link may get excellent bandwidth, if it's assuming that it doesn't stop and it doesn't have to wait for acknowledgement. But even if it does have to wait for acknowledgement, as we do in open atomic Ethernet, you don't lose any bandwidth. So the semantics experienced by the applications can be radically different. Let's move on to part 3 of the presentation right now, and let me ask if anyone has any questions at this point. So we're now moving into part 3, which I hope will be the most interesting and instructive part of the presentation. I'm going to try and disabuse this audience of their belief in a smooth monotonic model of time and show how the model in the Open Atomic Ethernet protocol builds causality from interactions, and notions of time and timestamps become, quite frankly, superfluous in a system design, all the way from chiplets to racks to rows and even entire data centers or between data centers. So this is a simplified picture from the Open Atomic Ethernet specification. It shows that the transmission of information is literally a sea of photons that fill the cavity in the transmit and the receive cavity, as you can see here. It doesn't matter if the channel is a copper cable, a printed circuit board, a fiber optic, or a terahertz tube of some conducting material like steel or something else. All electromagnetic energy travels in the field, not in the electrons. In a driven electromagnetic cavity, nothing moves through time. Energy circulates in the field, and photons fill the available modes of that cavity until absorption occurs. This is what we call reception. What we call transmission is simply the accumulation of sufficient energy and coherence at a boundary to trigger an irreversible electronic transition in the transistor, input transistor to the receiver. From a photon's perspective, there is no timestamp. There's no global ordering and no preferred direction, only emission, recurrence, and eventual absorption. There's directionally, memory and causality appear only when an interaction commits to a record and exports entropy. Time, in this sense, is not a background in which photons live, but the shadow cast by irreversible measurement. So let's go into dark mode here, because I really want to, in the next 2 slides, describe what is the most important aspect of, ever since I met Ahmed in, I think, 2023, when I say that timestamps are barking up the wrong tree. So let's go into nothing inside this cavity knows which end of the is transmitter. Energy flows through the electromagnetic field. Direction comes from boundary conditions. A bit is decided only when enough energy triggers an irreversible electronic transition. Now, seen this way, communication is not a forward march through time, but an alternating thermodynamic negotiation between emission and absorption. Each arrival of energy in the receiver locally reduces uncertainty by increasing what the physicists call mutual information. And that word mutual information appears in the distributed systems literature also. While each committed departure, each irreversible threshold crossing exports entropy into the environment, into this cavity, this alternating pattern of entropy decrease and increase is precisely what we call alternating causality. Causation is not a one-way chain ordered by clocks, but a sequence of locally reversible interactions punctuated by irreversible commitments. In OAE, we use something called perfect information feedback, or PIF, and this exploits this structure by refusing to collapse the interaction prematurely. Instead of discarding information via one-way decisions and timeouts, it preserves mutual information symmetrically through echo and reflection until commitment is unavoidable. In this sense, PIF is not a protocol layered on top of time, but a protocol that respects the underlying thermodynamics of information exchange, where causality emerges from conserved interaction rather than being assumed. So this is a key slide that I showed a couple of years ago, and I really want to emphasize why this is an incredibly important slide. So I'll bring up those transitions. The slide shows this category error that I want to make explicit. When we build clocks, including atomic clocks, we choose an accumulator that only increments. We decide in advance that time goes up, but nothing in the physics of the atom requires that choice. The transitions themselves are symmetric. The arrow comes from how we record them. Once every clock in the system increments in the same direction, we quietly slide into believing that there is a global background of time flowing one way. That belief does not come from physics. It comes from the design of our counters. We don't measure an arrow of time. We implemented one. We made it up. This is the arrow of time dilemma that the physicists talk about, but which computer scientists and networking engineers have really understood, and the most important thing that they can learn. And once we do that, everything downstream, timestamps, timeouts, causal ordering, inherits that assumption. This is not a bug in clocks or in the PTM structure in processes. It's a semantic mistake in how we interpret them. Monotonic clocks do not reveal an arrow of time. They impose one. So here is the statement, the important statement here. This category error that we commit treats the accumulator as a clock as evidence that time itself has a preferred direction. Atomic clocks transitions are monotonic by design, but that monotonicity is an engineering choice, not a property of spacetime. By aligning all clocks to increment upwards, we manufacture an arrow of time and then mistake it for a physical background of time. That background does not exist. So let's see if we can give you some more intuition about how you can think about this problem intellectually. When we remove that assumed background, we stop pretending that there is a universal arrow supplied by clocks. So then the question becomes, where does this directionality actually come from? The answer is interaction. Inside the photon cavity, there is no clock. There is no before and after in the channel. Energy flows through the electromagnetic field, and photons fill the cavity according to boundary conditions. Direction appears only when an interaction commits. When enough energy accumulates at the boundary to trigger an irreversible transition, that's what the OA protocol is designed to do. That commitment exports entropy, and that's where the direction comes from. This is alternating causality, the reversible interaction of the field followed by an irreversible commitment at the boundary. It's not time first, causality second, but causality first and time inferred afterwards. So what I'm showing you here is actually two ends of a pencil. And I'm trying to give you the idea that when something is arriving, when packets arrive on a network, you're looking at the point of that pencil coming at you. It's on its way to you. The orientation is from the transmitter to the receiver. So let's strip this down to the physics You can use this photon model as well, but a photon doesn't experience a ticking clock. It's emitted, propagates in the field, and is observed. There is no background inside the channel. So the opposite of that end of that directionality arrow is the eraser. What happens is when you have that packet depart the transmitter, this corresponds to energy exported to the environment, as in the second law of thermodynamics. Mutual information is conserved across the interaction. Time is not the conserved quantity. Information and entropy balance are. Let's take a look at this a little bit more about how we flip these. First of all, I'm pointing out that when that pencil starts coming towards you, you don't know how long it's going to be. You could have some slots that are very carefully designed so that you've got a Shannon alphabet on both sides of the link, and you try to match the size of the buffers. But you don't know whether that buffer, whether the packet's going to be a long packet or a short packet. And when it arrives, all you know is that you're receiving that point, and you don't know how long it's going to be. This is the big mistake that we make in networking by trying to assume that everything is streaming. Streaming is the enemy of transactions. You have to have interactions with what we call Shannon slots on both sides of the link that you can reconcile. So we don't know what the hell is going on underneath that alternating direction of the pencil. So clocks attempt to impose order after a fact. Links are where the order actually happens. If your protocol's correctness depends upon synchronized clocks, it is already misaligned with physical reality. Now, Landauer tells us the price of erasure. And what I'm pointing out here is that when erasure becomes unavoidable, if an interaction is perfectly reversible and there is no record is kept, it's not in memory anywhere, the entropy need not increase. That's what we know from quantum computing, and that's what we know from reversible computing, which is the kind of thing that Vera Computing is working with, and they've already taped out something which is fascinating in that they can harvest 50% of the energy normally lost to this erasure that we call. It's a causal decomposition of interaction that explains why time and memory and irreversibly always travel together. So this is compatible with time reversal, symmetric microdynamics, and with indefinite causal order. Time is not a primitive. Interaction is. Time, one of the things that we mistake is that when time stops because, the clock fails or the network fails, giving you updates, through GPS or whatever else, that assumption of holdover is part of the category error. Time does not stop. Clocks do. You cannot, assume that the universe continues counting something while you hold over. So this is one of the most important core diagrams from the alternating causality paper. This is a trapped informational loop that we implement in the Open Atomic Protocol using reversible state machines. This is a key picture. It shows why each party in a bipartite relationship, such as entanglement, where Alice and Bob are seeing the arrival of new information and losing information when it departs in the pencil and eraser model of time. What you're getting here is the orientation gives you this bipartite alternating of a sense of time. When you're just receiving information, like you are from GPS satellites on your iPhone or other phone, what you're basically receiving is correlations. You're not receiving information. The GPS satellite has no idea that there is a receiver. There's even one receiver, let alone millions or billions of them that are listening to those satellite signals. So the link to the paper is in the slide, and it can also be found on the itsabouttime.club webpage, which I encourage everyone to go and explore. So bottom line here, simultaneity is a myth. This thinking that from Alice and Bob of only a single direction of time is because we imposed an incrementing only counter on our measurement systems. this is the facade of Newtonianism. And some people might say, well, is this just Landauer? Well, as I said before, Landauer tells the price of erasure. What I'm pointing out here, that erasure becomes unavoidable when you're moving real information. If an interaction is perfectly reversible and no record is kept, entropy need not increase. So this is why we like to think about causality and information. Arrival versus departure. This is what I made obvious from the pencil and eraser model of time. The pencil points coming towards you. You don't know how long it is. There is no Bayesian belief behind that unless you build it into, the buffer sizes and the size of Ethernet packets and that kind of thing. So entropy accounting, the arrival of information corresponds to an information gain at the receiver. The receiver uncertainty decreases. In an information theoretic sense, entropy is the receiver's state decreases conditionally. This is you can model this with probability and with the high school algebra that is in Claude Shannon's seminal paper. And this is completely, as I've shown in this presentation, this is completely consistent with thermodynamics because the entropy decrease is local and conditional. This is the conserved quantity, not something that we call time that we inadvertently, always increment instead of decrement. Time is not a conserved quantity, information is. Interactions have counters around plus or minus zero, which is what we built into the ternary logic that's in open atomic Ethernet. This is not ever an incrementing monotonic counter. Now, when information departs, when you empty your SERDES into the cavity or into the environment, then what happens is you immediately overwrite that SERDES with the next slice that you want to put onto the wire. This departure corresponds to loss of accessible information. Any retained structure must be exported to the environment. This appears as heat and decoherence, which you could say is the erasure of, let's call it soft information here. So entropy increases globally when information leaves. This is what causes all of the excessive use of energy in data centers. But you don't know where that energy or information goes. That would be a God's eye view that we currently have in the second law of thermodynamics, or like the original law of law of thermodynamics. The way I think of this is if you have some photons that leave your body and they happen to arrive on a flower, that flower uses it to create more complexity and a more beautiful world. So we misunderstand the second law of thermodynamics by assuming that everything goes into these random microstates. It doesn't. Life in particular and all sorts of structures that are built in our environment, including crystals, actually decrease the entropy, but that comes from the information that you gave up into the environment. So mutual information, which is what we talk about if this is bouncing backwards and forwards in the open atomic Ethernet link, measured a shared structure between sender and receiver. On arrival, mutual information increases. The receiver entropy is conditioned on the sender, decreases, but on departure, as in the pencil and eraser model, mutual information collapses unless a record is maintained. Entropy is transferred into the environment. Mutual information is the conserved quantity across the interaction. What time is it? It's 11:43. Okay, I think I'm finished in a couple of slides. So there is no global clock required to define this process. What is conserved is information flow, in particular information flow from a stream of interactions, not just a blind streaming of bytes through a network. And it's conserved with this entropy balance that we maintain in the link. The link is silent until something comes in. The link is waiting for surprise. That's what Shannon information is. It's the answer to a yes/no question. And in the link, the question is, are you there? And the answer is, yes, I am. No surprise there. Um, but if something comes in and says, "Oh, I've got a real transaction that's coming in. I want to transfer this Ethernet frame, and I want to make sure the other side gets it," then all of a sudden now you've got real information coming in. You've got causal order, which is not imposed a priori. It emerges from this interaction structure. So this is completely compatible with the physics of indefinite causal order at the microscopic level. All we've done is we've engineered the reversible state machines into both ends of an Ethernet link. It's completely compatible with the theory of alternating causality, which is currently in peer review right now. And it's completely compatible with open atomic Ethernet. I think I've said this. I'm not going to say it again. Let's talk about this. Memory is expensive. When you have to remember everything, you've only got two choices. Well, you're going to run out of memory space, no matter whether you've got kilobytes of buffers or you've got megabytes of local NV of local memory, or whether you've got gigabytes of main memory, or whether you've got terabytes of storage. Doesn't make any difference whatsoever. Memory is expensive because we have to capture that knowledge. You might think that arrival of information, is ephemeral. If you didn't capture it, it's gone. Well, actually, it turns out that if you do use the SERDAS and the structure that we've built in networks to capture that knowledge, the knowledge might be thought of as the integral of information, for example, then we are starting to burn energy because you are saving things. So the big question is, are there other ways of saving energy that can, really start understanding the physics of the situations? But this also doesn't just explain why we've got this excessive amount of energy consumption in data centers. It also explains why high performance systems struggle with time and why distributed systems in particular struggle with trying to get the isolation semantics in transactions to actually work. The only solution to this semantically is exactly once semantics. In other words, it arrived exactly once, not maybe it didn't arrive, or maybe it arrived multiple times, and now you have to do reordering and duplicate detection at the application level. So what is the implication for these networks? Links, not clocks, should be the primitive abstraction. Mutual information, not timestamps, should define correctness. Reliability emerges from conserving information through interactions, not through retries. We know what retries do to us. You get retry storms that bring down the entire data center in these metastable states. So this aligns naturally with this echo-based symmetric link protocols like Open Atomic Ethernet. That's why we did this. Why we under the OCP-TAP community, we're trying to build an understanding of how this misunderstanding about the nature of time and this facade of Newtonianism actually will burn you, and it will cause your systems to fail. It will cause you to consume more power, and unfortunately, it's also consistent with buying more bigger, fatter networks, because when the only thing you've got to sell is bandwidth, and then you don't get to exploit some of these real interesting advantages that you have with networks. So takeaways include monotonic clocks do not reveal an arrow of time, they impose one. Information arrival and departure is a dual, it's a conserved process. Arrival reduces entropy locally, departure increases entropy globally. And mutual information is the environment that ties them together. This time is an emergent bookkeeping artifact of entropy flow, not as a fundamental coordinate that people think of in their head. So I'm now at the end of the presentation. I went 10 minutes longer than I expected, but I think this would be a good time for me to drop out of the presentation and ask if anyone has any questions.
Great. Yeah, open the floor for questions. We need some icebreaker. Hisham, you want to throw an icebreaker?
No, I don't have one now.
Maybe I finally stunned Hisham. So this is part of my plan over the past 2 years to try to um, educate the time appliance project into what is really going on here. Obviously, my preferred um, perspective is from a software company perspective because we're trying to make sure that transactionality is built into the networks themselves. And what I've been doing over the last 2 years is essentially trying to help this community, open the time appliance project, jump this chasm between Newtonian time, which is implicit in all human beings. We just think that one damn thing comes after another, and even our our emergence as a species depended for survival on being able to like predict the future. So we have all these reordering buffers that we have in our head that can correlate what's going on with what we see, with what we hear, and with a model of predicting, whether or not a predator is coming after us or whether we can find a mate so that we can propagate our genes. So that Newtonian view is a natural human instinct. And I've spent the last 2 years trying to unpick that instinct that everyone has. I've called it here in this slide the post-Newtonian, but the wilder relativistic one, which I've talked to Kevin Stampton about quite extensively, really is the beginning of like showing that that's not quite right. And this is relativity alone will actually prove or disprove the high frequency trading community. Another um, conveyor belt metaphor that I had a previous presentation on, I'm basically saying I'm taking your instinct that time always moves forwards and saying that when you deal in Newtonian time, it's just absolute time. It's changing the same everywhere. Infinite speed of light, flows uniformly in the same direction, like we assume. But relativistic time basically gives you the illusion that you've got all of these conveyor belts, and it's all moving in the same direction. So we've even got kind of a built-in assumption intellectually. Even if we know relativity, we can still kind of believe that this relativity gives us, a handle on being on sort of clinging to our idea that time moves, monotonically forward. But as soon as you bring quantum correlations into account, especially indefinite causal order, all bets are off. You cannot assume that all these conveyor belts, which are maybe all the observers that you're looking at, you can't assume that those conveyor belts are actually giving you a proper sense of the universe. It's 11:53. I've got 3 more minutes more. I'm happy to answer any questions here. I unfortunately got the announcements out of this far too late, so I didn't get my announcements on LinkedIn or on other places, Twitter. But Ahmed did that for me last night, and so at least we got a little bit of announcement. But the point is, I really wanted to get this video and the presentation of this logical argument, what I hope appears to be an impeccable argument. I wanted to get it on the video anyway, so that we can refer other people to this, and then they can come back. People like David Laravia can come back and tell me where I'm wrong. But I hope I've actually explained something that not only is that there's a problem with I'm trying to engineer simultaneity in high frequency trading, but there's an opportunity too. Once you realize that the high frequency trading industry is doomed, at least if it's relying on timestamps, we can then say, well, what would we replace it with? And anyone who's a deep expert in high frequency trading, and we know quite a few of those, we'll immediately say, well, okay, what can we replace it with? That means that that an awful lot of the fraud in high frequency trading no longer, will exist. And it also gives the whole market new opportunities to be correct. So I think that this is probably one of the most important presentations that I've given to OCP-TAP. And I've taken 2 and a bit years now to actually get all of this material into a logically consistent order on the OCP-TAP video set. And you can also find them on the It's About Time Club as well. We're currently revamping that website, and I will put all of my presentations on there. I've also put several other presentations from other people on there, so that they can so that things that are related to the solution can also be addressed. So it's 5 minutes before the top of the hour. I'm open to any questions. I've gone through part one, which is engineering simultaneity is ultimately a fraud. I've gone through part two, which is bandwidth latency and the collapse of meaning. One of the issues is thinking about time differently does give you an entirely different set of semantics that we can offer the database engineers. And then part three was the perhaps most difficult for everyone to understand. So I took some care to try to come up with some new explanations. The main slide is this one here about time doesn't flow like this. I'm going to take that away. And then the pencil and eraser view of time. So instead of these two flows, I actually realize now that I should have shown these two flows going in opposite directions in this pencil and eraser, this picture up here. But anyway, it's there. We've got them on the record. Any questions? David, have you got any questions? I didn't notice David at the beginning of this, so I'm not sure he attended the whole thing. He did get a pre-warning though that I was about to do some dismantling of the belief system that people have about high frequency trading. All right. Well, thank you very much, everyone. I really appreciate you listening to me. I hope that you watch this presentation again, look at the slides, go to the It's About Time website and start to look at some of the things that perhaps you in principle don't want to hear. But in practice, you will find that should give you some cross fertilization into the physics of this problem and give you and your companies and your investors an opportunity to invest in something that gets ahead of the market and does something differently.
Thank you very much, Paul. And we'll have, like, in 2 weeks another talk by Erza Varashi, and the title is a resilient and tail optimal RDMA NIC for distributed ML workloads. All right.
I'm looking forward to that. That's right up my alley.
Wonderful. So we'll see everyone in 2 weeks. Okay. Bye,
All right.
everyone.
Thank you, everyone.
Thank you.